Hey guys, so this is kind of an example slash lesson of Newton's law of cooling, and I chose a pretty hard problem to kind of model this around, so I'm going to explain everything with it. So a metal beam was brought from the outside cold into a machine shop where the temperature was held at 75 degrees Fahrenheit. After 10 minutes, the beam warmed to 45 degrees Fahrenheit, and after another 15 minutes, it was 55 degrees Fahrenheit. So use Newton's law of cooling to estimate the beam's initial temperature. So like I said, we're going to use Newton's law of cooling, although it also works for warming. Obviously, we're talking about warming in this problem. So this is kind of the differential equation that models this. So I want to take a second just to kind of explain everything with this so you get where this comes from. So this H has to do with like the temperature of the object. So this is going to change. And then this H sub S, so this is the constant surrounding temperature. So in theory, this doesn't change. You bring it into a room that's, like our example, 75 degrees. It's just going to stay 75 degrees. So that's a constant. That's important to remember. And then just to kind of, I guess, get the greater idea behind this. So what this is saying is that the rate of change with respect to time is proportional to the difference of an object's temperature and the surrounding temperature. So that makes sense. You know, the more time that there is, and you know, the more time that kind of goes on, you know, that's going to kind of help model how, you know, a temperature is going to go up or down depending on kind of the surrounding temperature that you're in. So I think intuitively this makes sense. So the question is, how can we actually solve this differential equation? So what I want to do is I want to just kind of walk you through this. So this is a separable differential equation. So I'm going to go ahead and solve it, and what I want to do is first I want to get kind of these H's together. So I want the capital H's together, and this is kind of just the path of least resistance to get those H's together. So I divide both sides by H minus H sub S, so then I have kind of this situation. So then I want to bring the dt over to the other side, so I can multiply both sides by dt. So now I've got this situation, and then I can integrate. So now if I integrate, so now I'm going to get the natural log of h minus h sub s equals negative kt plus c. And so now what I want to do is I need to solve for this h minus h sub s. So let's just focus on this for a moment. So to solve this, I've got to use e. So if I just use the actual definition here, so here's what this would simplify to if I bring e into this. And then what I want to do is I want to use the properties of exponents to kind of separate these exponents, like so. And I want to focus on this e to the c. So this just comes out to be some sort of constant. So what we want to do is, and if you watch my other videos, you know that this is kind of like the thing that I like to do. We rename these into something that makes more sense. So we're going to name it h sub 0 minus h sub s. Now, if you've watched my other videos, you might find this a little curious. But the thing is that you want actually, like, whatever you're naming that constant, you want it to relate back to kind of like what your output is. So this is helping us to kind of relate to our output, and the idea behind this is, so remember that h sub s, that's just a constant number. So keep that in your mind, that that's something constant, and then this h sub 0 is referring to the initial temp. So you want to have whatever temperature of the object that you're bringing inside, you want to relate that to whatever the outside temperature is that's surrounding the object. And so we really want to have both of these in here. Okay, so if I replace that e to the c now with this newly named kind of constant, here's how we can think about this. And so this is the solution then to Newton's law of cooling. So we're going to use this now in our problem. So a metal beam was brought from the outside into a machine shop where the temperature was held at 75 degrees Fahrenheit. After 10 minutes, the beam warmed to 45 degrees Fahrenheit, and after another 15 minutes, it was 55 degrees Fahrenheit. So I already talked about all that. Okay, so we're going to use this solution to help us with this. So first things first, let's think about this 75 degrees. So this is like that surrounding temperature. So that's going to go in for our h sub s. And this problem is actually pretty darn hard. We've got a lot of work, but I think this will really help us to kind of understand how some of these types of equations can work. So the next thing that we want to think about is this 10 minutes warm to 45 degrees Fahrenheit. So where is that going to fall into this? Well, 10 minutes has to refer to the time, and then 45 degrees, so that's referring to the temperature, like the temperature of the beam now. So if I plug that in, so here's kind of how all of that information is going to line up. And so remember, the point of this is we're trying to find the initial temperature. So now what I want to do is I really want to like solve for that H sub 0. And you might notice a problem with this, but just go with me here. We're going to resolve all of it in a moment. Okay, so I've got this situation, so I want to solve this for H sub 0. So let's see, first things first, I can complete my subtraction like this. Now I'm trying to get the H sub 0 by itself, not the K. So if I'm trying to get this thing by itself, I really need to isolate this H sub 0 minus 75. So what I'm going to do is I'm going to divide both sides by that e to the negative k. And then if you think about that, so as I've got this situation now, so think about this. This is a negative exponent, so what that means is I can bring it up to the top. And I'm going to use this trick more than once, so just kind of showing you where I'm simplifying everything. So now here's the situation, and so then just to finish solving for H naught, all I have to do is add 75 to each side. So there's my first solution. Okay, so now I noticed that there's this K here, but I'm going to just tell you, like, when things like this happen, you want to just keep going because we have not even come close to using all the information in the problem yet. So sometimes students will see this and say, oh, I think I'm doing something wrong. Don't like start worrying about that. See if you can figure out where this is going. This is a tough problem. So we'll figure it out. Onward. All right, so this is where we were at. We just kind of dealt with all this. So I'm just going to note kind of what came out of this little discussion. And now what I want to do is I want to move on to this 15 minutes. It was 55 degrees Fahrenheit. So before we go any farther, let's just make sure that we do clarify. So another 15 minutes means that we have that initial 10, and then we add 15 to that. So we're talking about 25 minutes in. And so now this is actually what I want to plug now into my equation. So I'm going to kind of plug all that information in, and now we're going to kind of repeat the same scenario where we want to solve for H naught again. So got everything set up here. I can go ahead and kind of simplify. So 55 minus 75, that's negative 20. And then I just rewrote this as negative 25k. So making our way towards trying to isolate this H naught, first I'll go ahead and I'll divide each side by that e to the negative 25k. Now in doing that, I'm going to bring this e to the negative 25k up to the top. So I have this expression, and then I can just go ahead and add the 75. So here is now my expression for H naught. So we found this first equation, and after the work that we just did, now we found this second equation, and I didn't write them in the same order, so sorry about that, but it'll be fine. So, okay, now the issue here was that we had this extra like k and h naught, so we couldn't get an answer, but now we've got two equations using all of this information, and so this is really like a system now, and so now we can actually solve for k by kind of leveraging this information. So these two h naughts, we can, because we have this information, we can now set the equations equal. So let's do that. So now I've got both sides of these equations equal. The 75s are going to drop out, so I'm just left with this negative 30e to the 10k and this negative 20e to the 25k. So I kind of want to work my way towards getting the k by itself. So I'm going to bring both k's to the same side by dividing each side by negative 30e to the 10k. And so when I do that, so I get this expression here, and now I can see that actually what would be better so that I can solve for k would be to multiply by 3 over 2. So I actually want to bring this over to the other side, so I'm going to have the reciprocal expression. So now I've got e to the 15k equals 3 over 2. And just one other note, I realized I didn't say this. So I used exponent rules here. So e to the 25k and e to the 10k, so 25k minus 10k, that gives me the 15k here. So hopefully that was clear. Okay, so continuing on, so now to solve for k, so now I can take the natural log of each side, and let's clear a little space here. So now I've got this, and so then I know just from working with natural logs, so I can bring that 15k down, so I've really got this expression. So then my k is really going to equal the natural log of 3 over 2, that divided by 15. And so we are almost done, we're getting close. So we had these two expressions, and now by setting them equal to one another, we found that k equaled this natural log of 3 over 2 over 15. So now what I'm going to do is I'm going to plug that in, and I'm actually going to plug it into both equations. This is just a really easy check to make sure that they match. So you can see now, so I plugged in my k, I've plugged them into both equations here. So with the first one, so I got 35.69, and then when I sort it out for the second one, I also get 35.69. So now we're good to go, and now we can finally say that the initial temperature was 35.69 degrees Fahrenheit. Whew, okay, so that was a lot of work, but hopefully this was helpful. Any questions, you can always drop me a comment. If you found this video helpful, please consider giving it a like, sharing it with a friend, or subscribing to my channel. Thanks for watching, guys. I'll catch you next time.